Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will talk about hypothesis tests for mu, where mu represents the mean of a normal random variable with known variance sigma squared. We have that assumption that sigma squared is known. Well, let's begin. So first, I would like to consider first a one-sided hypothesis test for mu. Okay? So let's just say that Bayesian one-sided hypothesis test for mu. Okay, so maybe, well, not maybe, I'm sure that you have done something like this in other introductory courses in statistics, but from a frequentist perspective. So we still are going to have that four-step procedure, but it's going to be slightly modified. Okay, so step 1 will be the same as for the frequentist counterpart. We state our hypotheses. So say for instance that you want to test H0, the null hypothesis, mu less than or equal to something. And the something is called mu naught, mu 0, which is the value under the null hypothesis, okay? And you want to test that one against the alternative. Your alternative hypothesis will be HA mu is greater than mu 0. Okay, so we have a one-sided alternative hypothesis. So now, step 2. In a frequentist approach, on the second step, what you would need to do is computing the test statistic. In this case, our step 2 will be finding your posterior distribution. Finding posterior distribution. Okay, and then step number 3 in a frequentist approach would be computing the p-value. Well, from a Bayesian perspective, step number 3 becomes find or compute the posterior probability of H0. Of your null hypothesis. Okay? Step number 4, your conclusion. When you did this from a frequentist perspective, was if your p-value is small, then you reject. Well, in this case, from a Bayesian perspective, step number 4 will be if the posterior probability of H0 is small, then you reject your conclusion. Okay, it's the same thing. Step number 4, same thing. You provide your conclusion based on the size of your posterior probability of H0 rather than based on the size of a p-value. Okay, so that's a basic idea. How about we talk about an example? Okay, let's try and apply that. Remember that we talked about an example when we talked about the posterior distribution for normal likelihoods, right? We talked about that parameter, right, mu, the length of trout, the average length of a particular kind of trout, right? And we had two experts, Arnie and Barb, right, analyzing the data, remember? Okay, so now what they want to do is, instead of computing a credible interval or finding just the posterior distribution for that parameter mu, right, the average length, they want to carry out a hypothesis test for that parameter. Okay, and as you can see, what we have here is another example of a one-sided alternative, right? They want to see whether or not the average length of that kind of trout is less than or equal to 31, against that average being greater than 31. Okay, so step number 1 is done for us, right? So let me copy paste this one somewhere else. Example. Step 1. What we have here is mu less than or equal to 30 against mu, well, it's 31, right? And 31. So that was basically for free. So what we need, right, is step number 2. That's the interesting part, finding the posterior distribution. So let me remind you what we did in this case. What we had, the data set and the priors that these guys considered, right? So what we had was Arnie, right, had a prior, a particular prior, a normal with prior mean 30 and prior variance, well, prior standard deviation, right, 4. Okay, and on the other hand, Barb was just considering a flat prior. Okay, so and then they had a sample of size 12, and the sample mean y bar well, happened to be 32. Okay, so let's just remember how we would come up with the posterior, right? Step number 2. Step 2. Find posterior distribution. Remember that in this case, when you have a normal likelihood and you're considering a normal prior with known variance sigma squared, what you have to do is first find the posterior precision, and once you have that, you find the posterior mean, and you find those guys using our updating rules. Okay, so let's find the posterior precision, and let me remind you that the posterior precision is just the reciprocal of the posterior variance. We're using S star squared to refer to the posterior variance, and remember that the posterior variance, the posterior precision, right, is the prior precision plus sample precision. And remember that since y1 up to yn have a normal distribution, that implies that y bar has a normal with the same mean as an individual observation, and the variance of y bar would be sigma squared divided by n. So the reciprocal would be n divided by sigma squared, right? Okay, so again, Posterior precision equals prior precision plus sample precision. Okay, and then once you have that, you can easily find the posterior mean. Posterior mean, m star, that's what we're using to refer to the posterior mean, is just going to be a linear combination, w, let me call that w, times m, where m represents the prior mean, and then 1 minus w times the sample mean. Okay? So it's just a weighted average between the prior mean and the sample mean, and that weight, that w, happens to be just that fraction, prior precision divided by posterior precision. That would be your w, that would be the multiplier for the prior mean, and then 1 minus w, well, would be the following quantity, would be n divided by sigma squared, which would be, right, your sample precision divided by the posterior precision, right? Okay, so once you have that, right, no problem, because we know that the posterior distribution in this case is normal. Posterior distribution, normal, parameters m star, that's the mean, variance s star squared. Okay, we good? Okay, so that would be step 2, right? So turns out that in the case of Arnie, right, the posterior mean is 31.96 and the posterior variance is 0.3265. So just let's copy that, right? Arnie's posterior, normal with mean 31.96 and variance 0.3265. And just a reminder that what we have here is mean and this is variance. Okay, so we are going to have something similar, right, for Barb's posterior. It's going to be normal, right, but since she considered a different prior, we are going to have different parameters for that posterior, right? So she considered a flat prior, but we know that our updating rules still apply for that kind of prior, for that flat improper prior. So in that case the mean is 32, that's the posterior mean, and the variance will be, let's see, after she applied those updating rules, 0.5774. Oh, that happens to be the standard deviation. So let me just make a note of that. So this one is standard deviation. Okay. Now we are in business. So we have step 2, right? Step 3, what we said is what we have to do is finding the posterior probability of H naught. Step 3, finding posterior probability of H naught, okay, or H0. Okay, so let's do this for Arnie first. So the posterior probability that you want is this. Meaning what you want is the probability that mu is less than or equal to 31, and you are assuming that mu has a normal with mean 31.96 and variance 0.3265, right? So we know that if we're going to be using a table, for instance, what we have to do is standardize first, right? So we just would need to subtract the mean and divide by the standard deviation. So we would have, in this case, right, it would be mu minus 32.196, so 31.96, and then 31 minus 31.96, and then we have to divide by the standard deviation, right? When we standardize, we have to divide by the standard deviation. So in this case, it would be, we would be dividing by the square root of 0.3265. So by doing that, what we have here is the probability that the normal 0, 1 is less than or equal to something. Let's do it using R, right? So what we would need is P norm of 31 minus 31.96 divided by square root of 0.3265. Okay, so roughly .6%, right? Note that what I did here, that intermediate step where I standardized, I turned this into a normal 0-1 calculation. I did that in case you have only access to a table, right? But if you have access to R, what you could do is you could use the p-norm function directly. So what we want is the area to the left of 31 for a mean, well, for a normal distribution with mean 31.96, and standard deviation, we don't have the standard deviation, right? We have the variance, the posterior variance, but it would be just the square root of that posterior variance. So we could place it here, and as you can see, we have the same result. Okay, so step 3 for Arnie is done. Let's do the same for Barb. Let's find the probability that mu is less than or equal to 31, but in that case, right, what we need is a different normal. We're going to be considering a different normal. She used a flat prior, so she ended up with a different posterior, right? So let's just repeat this. So P norm, we want the area to the left of 31. In this case, the mean is 32 for Barb. And the standard deviation, in that case, we have directly the standard deviation. So it's just 0.5774. 0.5774. And note that we end up with basically the same posterior probability for the null hypotheses, right? Step number 4. Conclusion. Let me just say this. If your posterior probability is small, then reject H naught. Right? So, for instance, we could take an approach similar to the one that you would take if you were doing this from a frequentist perspective. We could give a cutoff, like a significance level, right? So what we do there is, if your posterior probability, say for instance, if the cutoff is 5%, if that's a significance level that you're considering, then you reject, right? But note that the Bayesian perspective gives you something that is also really interesting. Note that the complement of this probability gives you the probability of the alternative, right? So the probability of the alternative would be roughly 95 point something %. So what we can see is that this that the alternative has a much higher posterior probability. So this one makes more sense, right? So you could state your conclusion in terms of that the alternative is much more likely than the null, right? And you could use that posterior probability to give an idea of how much more likely is the alternative, right? Makes sense? So in this case, you could say something like, and note that the probability of the posterior probability of the alternative is roughly 19 times the one of the null, right? And then you go, oh well, it seems that the alternative is more consistent with the data, right? And not just give your conclusion in terms of either you reject an H naught or you fail to reject H naught. Okay, and something else that is really nice is that in this case, this is the probability of the null, and the complement is the probability of the alternative, right? And p-values don't have that sort of direct interpretation. Okay, now before we finish this video, I would like to say something about two-sided alternatives. Okay, so what you do if you want to test a two-sided alternative, right? Well, first what you have to recall is that in this four-step procedure that we described here, so you find your posterior distribution here, step 2, and then step 3, you find the posterior probability of H naught. But think about it, if your H naught is just 1 point and you have a continuous probability density, right? So the probability of a single point is 0. So you can't find the probability of this single point, right? So how you go about that, how you go about testing a two-sided alternative from a Bayesian perspective? Well, what you have to remember is that there's a relationship between a two-sided alternative and a credible set, or back then when you were doing frequentist statistics between two-sided alternatives and confidence intervals. So you can compute confidence interval to carry out that test, and that's how you would proceed in a Bayesian perspective, right? And if you want to test a two-sided alternative, what you do is you find your Bayesian credible set. If the value of the null, if the value of the mean under the null hypothesis is not contained inside your credible set, then you reject. Okay? Make sense? So that's the only difference. That's step number 3 here. When you have a two-sided alternative, here what you have to do is instead of finding the posterior probability of H0, you find the credible set. Okay? And that's what we have here. Basically what we said, that we can't find the probability of evaluate the probability of a single point if we have a continuous probability density function. So what we have to do is compute the credible set, right? And then if mu naught is not contained in that credible set, then you reject. Make sense? And of course, if it is contained in the Bayesian credible interval, then you can't reject H0. Okay? Well, that's it. So let's just summarize what we did here. So we talked about hypothesis tests from a Bayesian perspective. So it's a very similar 4-step procedure, right, to the frequentist 4-step procedure that you have seen before. It is a slightly modified version of that 4-step procedure. First one is the same. You state your hypothesis. Step number 2, instead of finding a test statistic, you find the posterior distribution. Step number 3, instead of finding a p-value, you find the posterior probability of H0. And step number 4, well, based on the size of that posterior probability of H0, you provide a conclusion. If that posterior probability of H0 is small, then you have strong evidence to reject H0, right? And what we said is that if instead of considering a one-sided hypothesis test, you're considering a two-sided alternative, right? What you have to do here is modify step number 3. Instead of finding the posterior probability of H0, because that would be just a single point and that would be 0, what you do here is you find the Bayesian credible set, and then if mu 0 is inside the credible set, you fail to reject H0. If H0 is outside that Bayesian credible set, then you reject H0. Make sense? Well, that's it. Well, thank you so much for watching. Please take care and keep working hard. See you next time. Bye.